Okay, depending on when you're watching this video, you may or may not have done this warm-up. So if you did do the warm-up, go ahead and listen to this explanation. If you didn't, just fast forward to the notes then. So in this one right here, describe the scatter plot. So there is a weak negative linear relationship here. It says in the problem, assume conditions have been met. It does say, does it reduce? So if it's reduced, it's negative. Again, make sure you're defining what B is. So true slope of the regression of corn yield on weeds. If this is a t-test for slope, I said the conditions were met. I just took the t straight from there. I took the p-value, divided it by 2, got that there. It told me here to use 0.05, so the p-value is less than alpha. Reject HO. There's enough evidence to say that more weeds reduced corn yield. Okay, this next lesson here. Not really one of my favorites, but something definitely a little bit different here. All right, so the idea here is that obviously sometimes data is not linear. So if data is not linear and we want to try to fit a line to it, we need to come up with a way to do it. So there's two approaches that we could take. One approach is that we try to use one of these other numerous regression options that we have. So that would be one way to do it. The other way to do it is to transform the data and make it linear so we can use our familiar StatCalc8. Given the title of this chapter, it should not be a real surprise that the approach that we're going to use is we're going to transform it so we could still use our StatCalc8. When we transform this data, we're going to end up with two different ways of going about it that we're going to speak of. Obviously, there are more options, but we're just going to focus on these two in this section here. So we could have a power model or a power relationship, or we could have an exponential model or an exponential relationship. This first few pages here are focusing on this idea of the power model. The most important thing for you to know is that you do not have to take a data set and try to figure out how to transform it. You just need to be able to look at a data set and figure out what the transformation was done and use the transformation, right? So a power model is y equals abx. So if you notice, the x is raised to a power. You could also raise the y to a power, so we'll do both of those things as well. There are some examples in your textbook on page 768. There's distance, time, period, intensities, those kind of examples and stuff if you want. This one right here, so this example, it says, what does a country's under 5 child mortality rate tell us about the income per person for residents of that country? Here are the data for a random sample of 14 countries in 2009. Create a scatter plot of the below data. So if you look here, we've got these different ones right here. So we're going to I'm going to type those numbers in. I haven't yet typed them in. So you go ahead and type those in as well. These are ordered pairs, so they've got to stay together. We can't split them up. Over here I got my income. Sorry, usually I'm more on top of things and I type these in ahead of time, but today, guess I am not. All right. Okay. So it says right now to interpret the scatter plot, so I'll probably figure out right now if I typed in anything wrong. There's my L1 and L2. I'm going to hit my zoom 9. And there's my scatter plot. That's how it's supposed to look. So there is a strong negative non-linear relationship between under 5 mortality rate and income per person. All right, so the first thing that we're going to do, so obviously right now it's not linear, so I need to transform this data to make it linear. So the first thing that we're going to do is we're going to apply a transformation to the child mortality rate. If you notice here, I'm raising it to the -1, which essentially means that I'm taking the reciprocal of it. So I'm going to have 1 over the child mortality rate. So the mortality rate is my x variable. So on my calculator, I'm going to go over to L3. I'm going to use my up arrow. Black box there, I'm going to press enter, black box blinking down there. I'm going to do 1 divided by L1. So that's my new x variable. Now what I want to do is I want to look at that scatter plot. Now when I look at that scatter plot there, so I want to look at my new variable, my new x, which is 1 over L1, or 1 over the original x. So that's why I'm putting L3 there. I'm leaving the y, I didn't transform the y. If I look here now, so it says create the scatter plot and interpret the plot. So now I can say there is a strong positive linear relationship between the reciprocal of under 5 mortality rate and income per person. All right, I only transformed the y variable here. Okay, so what that means is that if that works, then I can use my familiar StatCalc 8 to create an equation now. So what they did here is that they actually have 2 separate Minitab outputs here. So in this first transformation, this is the one that we just did in the first page. So they did 1 over x, comma the y. So again, this first line still relates to your intercept, and this line still relates to your slope. In the second transformation, what you notice here is that they didn't transform the x variable here, they transformed the y variable here. But again, this still relates to your intercept, and this one still relates to your slope. So back up here, or actually, let's go down here. It says here, do the following for both transformations. Give the equation of the least square regression line. Define any variables that you use. So I kind of tried to just define my original variables. So the x is the under 5 mortality rate, and the y hat is the predicted income. I try to do it this way because otherwise you'd have to define 4 variables. You'll see what I mean. So the first one, the first equation, I didn't transform the y. So I would have y hat equal, and then there's the 869, that's the intercept, plus there's the slope, but this one is 1 over x. In the second one, I don't have y hats, I have 1 over y, but there's a big hat, so it's like 1 over y hats, I guess. There's 5 zeros there after the decimal. Again, I think there's 5 zeros after the decimal. And the x was not transformed here. Alternatively, you could do this as income. No, this isn't income. This is under 5. No, this is income. I was right. Income, and then you could do like 1 over under 5 mortality. So if you wanted to write it like that, instead of defining things later on, you could always do that as well. All right, then it says to predict the income per person for Turkey, which had a child mortality rate of 20.3. So then I'm going to take the equations that I had in the first page. So the first one, and I'm going to do 1 over 20.3, and I plug that in, and I get this value right here. And then for the second one, this is the one with all the little zeros. So what you just don't forget, some of you kind of forget how to do your algebra on this particular one. Times that 20.3. So 1 over y is equal to this. So that means y, if I'm like, this is like over 1, so if I cross multiply here, so then I'd have like that big number here. So this big number is going to be here, and it's going to be equal to 1. So then y, I did that. So y ends up being equal to 1 over this like number right there. So if I do 1 divided by that, in this case, and this is the predicted, I should keep that hat there because it's the predicted, it's not the actual. So that would be the predicted for that one, okay? Okay. When we do the interpretation here, there's some things that can stay the same, some things that will have to change. So the first one, it says to interpret r squared, so there's the r squared. So for the first one, I'm going to say that 84.3%. And then the parts that are kind of staying the same is this part right here. So of the variation. So that part is the same. Remember, it's always the variation in the y variable. So in this case, it's income. And then this rest part right here is kind of the same. So is accounted for by the regression of, and again, you're always regressing your y, so income on, and it's always on your x variable, and the x in this case is the reciprocal of mortality rate. And then when I do the other one, so the stuff that I wrote in gold is kind of going to stay constant. So the other one is 92.1. So 92.1%. So again, of the variation in, now in this case, it's not income for the next one, it was the reciprocal of income is accounted for by the regression of, and again, now the regression, the y variable is the reciprocal of income on the mortality rate. The mortality rate was not taking the reciprocal of for this one. All right, so I tried to keep this stuff in gold. That was the same for both statements. All right, so sometimes you might be asked which transformation is better. So again, it's not like I gave you the data set and said, figure out how to transform it. I said, okay, it's been transformed for me. Can you write the equation? Can you interpret the r squared? Can you make a prediction? So those are the kind of things you're going to have to do. Maybe you'll be asked which one is better. So obviously we can look at the r squared. So this one is doing a much better job of explaining the variation. Another thing we can look at, the residual plot, is I would say this one has a little bit more scatter than that one does. So the second transformation is probably doing a better job with our prediction here. All right. So basically that first 2.5 pages there was kind of just giving you an introduction of what's going to be happening here. Now what we want to do is we're going to switch gears a little bit and try to compare the two options that we have here. So we could have a power relationship, or we could be doing an exponential relationship. Those are the ones that we're going to focus here in the AP class. So the problem with a power relationship is that we have lots of choices here. So there's lots of different powers that I could choose here. So in this particular one, we just did the reciprocal. So we just took it to the -1. Another option is maybe I want to square something. That would be raising it to a power. Maybe I want to take a square root. That's raising something to a power. So there's so many different options for powers. So how do we know? So is there an easier way? So there is an easier way. And this involves logs. So just a thing to note here. So log is base 10, remember? And ln is base e. But all your properties of logs and all that stuff is the same if you're using log or natural log. I'm going to do these problems here with log, but technically I could also use the natural log. All right, so what I'm going to do here is, let's see what happens here if I take the log of both sides. So if I take the log of y and I take the log of the other side, x plus b. Okay, so if you remember your properties of logs here, this is still going to be log of y. And then if you remember your properties here, you split that. Don't worry, if you don't remember, I'm not going to ask you to do this ever later. They're probably not going to ask you on the AP test. That wouldn't really be a great use of their time. On your calculus AP test, perhaps, but not in the stat one for sure. Also, if you remember that b comes out front. Okay, if we remember our properties of logs, and I'm sorry that I'm not going to be very original here. This right here, if I take the log of a constant, I still have a constant. Okay, so what's going to happen over here is I'm going to have the log of y, because y is a variable. And then this is where I'm not being original. So the log of a, I'm just going to say it's still equal to a, even though it's not. Pretend it's a different a. And then I have plus b log of x. If you notice here, this looks kind of like my y equals a plus bx, right? Because I've got the intercept and I got a slope. So basically what I did by taking the log or the natural log of both sides, so if I take the log, natural log of both variables, I end up with a linear relationship if the original relationship is a power relationship, okay? So the big idea here, so therefore, if two variables have a power relationship, you can make the relationship linear by taking the log or natural log of both variables. Okay, so that's the idea here. That's one way. Instead of me trying to figure out, should I square it? Should I take the square root? Should I take the reciprocal? I could just take the log of both variables. All right, an exponential model. So an exponential model looks a little bit different. An exponential model, the x, the variable, is the power. So examples of that, like your compound interest, your radioactive decay, so things like that. I'm going to do the same thing here. So how can I linearize an exponential? So again, I'm going to do the log. I could use the natural log though. You would just undo them different ways. That's one thing you're going to need to remember. Oops, I wanted to make that gold again. Okay. Split those up like we did before. the x comes down. Okay, so just like before, the log of a, constant. It's a constant, so when I take the log of it, it's a constant. B is a constant. So if I take the log of b, it's a constant. So now what happens here is I have the log of y is equal to a plus x times b. I'm just going to write it as bx. Again, looks very similar to our y hat equals a plus bx. So therefore, if two variables have a exponential relationship, you can make the relationship linear by logging or natural log the y variable only. Alright, so we only need to transform the y variable. Again, I am not going to give you a data set. The AP is not going to give you a data set and say, figure it out. They're going to already have done it for you, and then you just have to figure out afterwards what was done. All right? So just like this next problem right here. So this is about M&Ms. So we got a student opening up a bag of M&Ms, dumping them out, eating all the ones with the M on the top. When he's finished, he put the remaining 30 M&Ms back in the bag and repeated the same process over and over until all the M&Ms were gone. Here is a table and a scatter plot showing the number of M&Ms remaining at the end of each course. All right, so after his first dump, 30. After the second dump, 13, and so on, all right? So since the M&M should be cut in half at each course, an exponential model should describe the relationship between the variables. So then it says after applying the natural log. Remember I told you the natural log base 10, we could use any of those things, all right? Of the number of M&Ms remaining, here's the scatter plot of that versus course number. All right, so like I just said, it's going to say to you, can you figure out what was done? So it just tells you right here, they did the natural log of number of M&Ms remaining versus course number. If you look at the scatter plot, it's just the natural log of remaining. Again, the x variable has not changed. So it says the last observation in the table will not be included since the natural log of 0 is undefined. Interpret the scatter plot. So I could say there is a strong negative linear relationship between natural log remaining and course number. And says, would it be reasonable to use an exponential model? Yes, an exponential model would be reasonable. All right, again, the reason why I'm saying this is because when they took the natural log of just the y variable, I am now seeing a linear relationship. If they had to take the natural log of both to get that linear relationship, then it would not be reasonable to use exponential. It would be reasonable to use the power. All right, here's the Minitab output. Again, you can use this with x and y. Just make sure you define them, or you could do, just the words. So natural log remaining, put a big hat over it, equals, there's my intercept. And then times the course. If you wanted to do it with variables, so again, you could do it with variables. If you notice here, what I did here is I did a predicted natural log of the number of M&Ms. If you only wrote y hat there, just say the predicted number of M&Ms, just make sure you're defining whatever it is that you wrote on that side there, okay? Then it asked me to use it to predict the original number of M&Ms in the bag. So the original number of M&Ms in the bag is going to be when I'm at course 0. So what's going to be happening here is I'm going to plug in 0 here, so this is just going to be plus 0, so that's kind of irrelevant. To undo the natural log, if you don't remember, this is when you have to e both sides. So basically what e I want to use is the e that's above that natural log button right there. So see that e right there, this little e there, so I want to hit second natural log. And when I do that, what I want, well, it's nice to see the sun. It's kind of disrupting my video here. So what I want to do is I want to e both sides. So I want to do that 0.40593. So the predicted remaining at course 0 should be 57.93. Again, that would be your y-hat if you did it that way. All right, look at the residual plot of the linear regression in part B. What does this graph tell you about the appropriateness of the model? Again, this is the residual plot using course and the natural log remaining. So if I look here, I could say that a linear model is appropriate for natural log of number of M&Ms remaining and course because there's no pattern there in the residual plot. Okay. All right. How do you decide if a power or exponential model is better? So remember, the power is when they did the log or natural log of both variables. Remember, the exponential is if they just did the log or natural log of the y. So how do you decide if it's been applied? Just look at that. How do you decide which one is better? Then look at your r squared. Look at your scatter plot. Look at your residual plot. The same things that we usually look at. So here's the original problem, and it's just another way to look at it. So if you notice here, so the original problem, it's the under 5 mortality and the income per person. And then what do we have here is we have the under 5 mortality and we have the natural log of the y variable. Here we have the natural log of the x and we have the natural log of the y. So this one is doing the exponential model. This one is doing the power because they've done both. All right. So then when it asks me on the next page, so just right here, which one looks a little bit better? I mean, they're both pretty good. This one probably, if I had to pick between the two of them, I'd probably pick this one. This one looks a little bit straighter. All right, so the next page, it does say, explain why a power model would provide a more appropriate description of the relationship between income per person and under 5 mortality rate. And again, right here, because that scatter plot is showing a strong linear relationship. All right, so what I set up here, this scatter plot is showing a strong linear relationship. Why don't you go ahead and pause the video and try the last few problems right here. And then when you're ready, unpause it and I'll go over my answers. So here's my equation. Again, this one we decided it was power, so both variables are taken the natural log of. There's the coefficient. There's the slope. I wrote both of them as natural logs. If you're not going to, don't write the word natural log there. You do have to take the natural log of 20.3. And the last one that we did, we plugged in 0, so there was nothing to do there. So you do have to, so kids kind of don't always do this one right. So you need to make sure, the way I got this 8.675 is I did 11.4950 minus 0.93740 times the natural log of 20.3. So that's how I got that there. Then you e both sides, you got that. Here's the residual plot for that regression right there. So since there's no pattern, the power model is working well. Okay, now those 3 problems for the homework, don't make them hard. Again, you're just trying to figure out what was done. You don't have to come up with anything on your own.